Hi, I'm Randall Heyman, a mathematics academic. I was concerned that during the coronavirus outbreak, many students would have their learning impacted by the outbreak. So I'm making these quick turnaround videos to help. I've even got rid of the YouTube advertising, which can be quite annoying. So if you'd like me to make a video for you or your students, comment below this video, or in fact any of my videos, or drop me an email to coronahelpmathematics@gmail.com. So we're stepping through Euler's theorem, sentence by sentence. And in the last one, I just had a little tangent off where we used Maple to explore how Euler's theorem actually works when you put in real numbers. Anyway, we're up to now the sentence that says, since this group has order phi m, the order of R is a factor of phi m by theorem 10.15. So what I'm going to do now is I'm going to go to my whiteboard. So we'll go to new share and go to here. So you should be able to see this. This is a bit of a busy screen, I'm afraid. Let's just get rid of this up here. So we've got, well, I've just got the theorem. That's what I'm doing here, Euler's theorem. This is the sentence that we're looking at. This is the theorem that it refers to, and this was left over from last time. So here's the problem that a lot of people are going to have. The problem is that the order means different things in respect of a group and in respect of the element of the group. So if we go down here, we've said that R is an element of, what's actually an element of this group, which is here the set X, where 1 is less than or equal to X is less than or equal to M, where the GCD of X and M is equal to 1. And we use multiplication modulo M. So let's write a few things up here. The order of a group G is the number of elements. Of G. And here, in the case that we're here, the order of G equals phi of M, because remember, we defined phi M, the Euler totient function, value M. We defined that previously, actually, as being the number of elements of this exact set. So that's fine. Now, what's the order? Here's the catch. The order of R, which is an element of G, is the smallest value, call it T, such that R to the power T is equivalent to 1 modulo M. Okay, so example, M equals 10. So in this case, G, what's G? G is the set, or the group. I'm being a bit vague here, but it's all the elements between 1 and 10 that are co-prime to 10. So 1 is co-prime, 2, 3, 4, 5, 6, 7, and 9. These are the elements. So if you like, we would say that the order of G, of the set G, is equal to 4. Now, let's look at the number 1. Well, 1 to the 1 is equivalent to 1. So, whoops, let's stick in blue. Let's try and be color coordinated. 1 and 1 is 1 mod 10. So order of 1 is, in this modulo 10 world, is 1. What about 3? Well, 3 to the 1 does not equal 1. 3 squared equals 9, which is not equal to 1. 3 cubed equals, well, equivalent to 27, which is actually in mod 10 world is 7, certainly not 1. 3 to the 4 is 81, is 1. So the order of 3 is 4. What about 7? 7, well, 7 to the 1 is just 7, that's not equal to 1. 7 squared is 14. 14 is 4. 7 cubes not going to work. I don't even know what it is. 243, I think it is. 49. Actually, this one should be 9, isn't it? Shouldn't it? Sorry. 7 squared is 9. 7 cubed, yeah, will be 9 by 7, which is 16, which is 6. I think that's right. And 7 to the 4 is, well, 7 squared over here is 9. 9 nines are 81, so that'd be 1. So the order of 7 is 4. It took to getting up to the 4th power before we hit 1. And the final one that we could look at is 9. 9 to the 1 is 9. That's not equal to 1. But 9 squared is 81, which is equal to 1. So the order of 9 is 2. Now, if you look here, you can see what we've sort of, one, I've shown you how to work out the order for any element of a group, but you can see here 1 divides 4. See this 4 up here? That's the order of the group, 4. So now working out the order of the elements, 1 divides 4, 4 divides 4, 4 divides 4, 2 divides 4. So in the case of 10, it certainly works. And that's exactly what theorem up here, theorem 10.15 is saying. So let's go back to the sentence that we're trying to come to terms with. So so we're up here now, since this group, whoops, yeah, since this group, why doesn't that work? Since this group has order phi of m here, the order of R is a factor or a divisor of phi of m by theorem 10.15. And you can read 10.15. So that tells us, that basically explains that line. I think I'm pretty comfortable with that. I hope that's clear to you. Now, just before we go, this theorem here. Now, you've got a choice here. You can just accept the theorem as is. Just take it as it's like a black box. It's told you the answer, you've used it, move on with your life. Don't waste any more time on it. Your aim was to understand Euler's theorem, and you can understand it just based on the fact that theorem 10.15 is true. Now, if you want to go into do more detail and spend more time, you could try and come to terms with theorem 10.15. It's a very beautiful theorem. It's a very useful theorem actually in abstract algebra. So it's worthwhile. The other thing is, if you're following what I'm doing, then theorem 10.15 up here, yeah, is not too hard. It's not too hard. But I'm going to skip over it at this point. We want to keep our eyes on the main game, which is Euler's theorem. And so I'll just skip over I'll just take theorem 10.1 as read, as a given, and we've come to terms with this sentence that we wanted using 10.15. We'll leave it at that. But if at any stage you want me to go through 10.15, then leave a comment below this video or send me an email. I'll just roll up here and you can see my email address. There's the email address here. But of course, any other questions on any mathematics, whether it's university level, high school or primary school, happy to help. So just comment or drop me an email.